at point B. So this will be equal to your Vy. Your Vy is equal to 90 times 10 to the power 3 divided by your IZZ is 5.8133 times 10 to the power minus 6. Okay, so VQ is equal to 60 times 10 to the power minus 6. Thickness 0.02 multiplied by 2 again. This is because of your left and right. Okay, so this will be equal to 90, 60 power minus 6 divided by 5.8133 power minus 6 divided by 0.02 divided by 2 is equal to 23.222 times 10 to the power 6 Pascal. Okay, so that is your stress at point B. Then again, I'm going to use the same equation. Okay, so if we are going to apply this self-equation again, all right. So if I'm going to apply, like something controlling the computer, right? So if I'm going to use this equation, right, we're going to apply this equation. So at point B now, y will be equal to what? Y will be equal to 0.035. So it's 65 minus by 0.03. Someone has a question. If you have a question, ask me now, please. Anyone? Okay. Sorry, minus by 0.0. Anyone have a question? Yeah, okay. Someone unmute the mic. If you have a question, please ask me. Yeah. So 0.035 meters. So you substitute this equation now. The answer should be the same. So the shear xy from the above equation at point B is equal to 32.705 times 10 to the power 6 minus by 7.7409 times 10 to the power 9 multiplied by 0.035 squared. Okay, so 0.035 squared times by 7.7409 power 9. Then you get 32.705 power 6 minus by the expression. Oh, syntax error. Sorry, my bad. Minus by 7.7409 power 9 times by 0.035 squared. So it's 33.222. The same. Okay, 23 times 10 to the power 6 Pascal. Okay. So that's why I picked this example. Okay, this example, it seems confusing and tricky, but if you apply the rules, it's not so bad. At point A, what you have learned down here, if you want to calculate point A, the thickness, you use the minimum thickness because it's the higher value. Why the higher value? You can see over here, right? Once it reaches the web, it seems that it has a step function. Okay, it goes straight up, right? So you calculate the higher value. And then the next thing to learn is you want to take point B, right? So you have to take point B. If you choose the wrong area, find the wrong first moment of area, it's not going to work out because one of the rules that is specified is the first moment of area region cannot cross or intersect the centroid. That's why you have to start from the bottom. It is very abstract because your shear force start from the what? Start from the top. It's so mechanical engineer, right? Seeing is believing. If we start from the top, I have to start from the top, right? Not for this case. Okay, this case is not for this case is because of how we derive the first moment of area. Okay, so I hope you all will embrace these 4 rules. Okay, you will look at these 4 rules. You can handle any questions now regarding shearing stress, and I'm going to prove that to you. Before I go on, we're going to start a new section. Any questions, please?
Eugene.
Yes.
So we'd only use the QZ for the flange if we're looking at a point within the flange.
Okay.
Because earlier in the example, last week you calculated QZ for the flange.
Yeah. So we did not know. We did not need to know what is in the flange for this question.
Okay.
Okay. So I have a question that's asked that on the test, should we use the distribution equation or the regular equation? I will tell you what to derive. Okay. If I want you to derive the equation of the distribution, I'll tell you. If I want you to have a specific location magnitude, I will tell you. Does that make sense? Yes?
Sir,
Yes.
no, if on the same question, you will, let's say you ask us for a certain point, but I use distribution and then I plug in that point instead of using this QZ from scratch again. Is that okay?
Yeah. This to find out about specific point is very much quicker, right?
Yes.
Right. So if the question again, if I ask you to derive the equation of the distribution equation, you have to derive. If I don't ask that, you don't need to do it.
Okay.
Okay. Now I'm teaching. Okay. I want you to see both. Okay. That's why I'm doing both. Right.
Okay.
Okay. Any other questions, please? Good questions. Okay. Good questions. Anyone else? No. Okay. So you have to be very, very careful to look at. As I say, I make this mistake. Okay. Not being mindful. Okay. I make that mistake. Right. So the next. So this is what we have done. We have completed what we call shearing stress. So this is a complete of shearing stress.
Eugene,
Yes.
just the last question.
Yes.
So if the question asks that just find the maximum shear stress, regardless of where the point is, it will be at either one of those points, right, where the flange meets the web, like either one of the.
No, the maximum shear stress will always be at the centroid.
Oh, okay. So
right? Because when we derive, look at over here, the tau max is always at the what? Centroid, right? And if you look at this expression over here, right, which I'm circling now, like this expression over here, the maximum value will because this is minus over here, the maximum value will occur where is what? 32.705, right?
Mhm.
Where is y equal to 0. When y equal to 0 is at the where? Centroid. Does that make sense?
Right.
Okay. Okay. So this is the end for the shearing stress in the thick wall. Okay. So you should be fine doing this. All right. Let's start building decks now. Okay. This is where things get interesting. So the next section is longitudinal shear. Of a beam section. Okay. So when do we apply this analysis? Okay, when do we apply this analysis? So it's to analyze.
Is this when the beam is being stretched?
Say it again.
Is it when it's like being stretched when it's going the opposite direction from the
How do you mean?
parallel?
How do you mean it's been stretched?
Isn't that longitude? Like in that direction?
No, this is the tighter.
Right.
Okay, so this is a tighter, and is when we apply longitudinal shear of a beam section. Okay. Hello.
Yeah, I
Okay.
muted my mic.
Okay, so to analyze, so longitudinal shear of a beam section is to analyze the strength okay, of the joints in the shear loading. Okay, the emphasis is on the joints. Okay, again, I repeat, the emphasis is on the joints. So the joints right? The joints can either be glued together, bolted, screwed, nailed, whatever you want to be. Okay, so if we were to draw a structure, so this is X, this is Y, this is rotation in the Z. And then we have our beam, right? So this is our beam. And our beam for this case is simply supported. So if we look at the cross section of our beam, so we decide to do a section at an end section. Okay, so we slice it up, and in the end section, right? So this will be our Y, Z, rotation about X. Okay, so our beam, we do something special. What is this special thing we do? Our beam will have made of several components. So this is one component. This is the other component, right? Then we decide to do something fancy, right? So we want our cross section to look like this, okay? But we want to make it in such a way that it's difficult to cast, okay? This is ideal for wood. We want to make it like this, and then we want to do this, okay? Fancy shape, okay? Aesthetically looks good, but physically I'm not sure. Maybe, yeah, it can be aesthetic also. So we realize that, hey, we want, so at this point that I'm drawing now, I want this to be nailed. Okay, over here I want it to be nailed, and then not only do I want it to be nailed, over here I also want to be glued. Right, then down here at the bottom part, you realize that it's getting expensive. You just realize, okay, maybe down here I'll just glue, or maybe down there is below water, and you realize maybe I'll use glue. It can seal it. If I nail it, it will not. You're not seal it. Okay, so you just want to be glue. Okay, so all these are. So over here, this is nail. And when we nail anything, right? It has to be. We have to know a certain what we call spacing. So the distance from here to here is, I call it S. S is the spacing of the fastener. Okay, so it can be bolted, screw, or nail. What is this spacing? Okay, now question, if we look at the end section, where is the first region that this cross section is going to fill? Can anyone tell me, please?
Where it's nailed?
Yeah. It's always at the joints. Am I right? You're absolutely right. Okay. It's always at the joints that it will fail. That's why if you're going to confront some